Okay, so we're going to be talking about, again, exponential growth problem. And here in example 4, we're going to be choosing a base for an exponential equation, right? Here's the problem. It says at the beginning of the summer, the population of a hive of wasps is growing at a rate proportional to the population. From a population of 10, so it starts at 10, on May 1st to, that's supposed to be 50, not 550, 50 in 30 days, how long until the population reaches 100? Okay, so it's growing proportional to its current population. So we got to think of it this way, right? Our initial amount, y0, is going to be 10, right? That's what we know, okay? We also know that after 30 days, right, it's going to be 50. Okay, so this is how I would do it. I would say there's a couple different ways we can do it, but this is how I would do it. I would say 50 is equal to 10 times, okay, times some b to the, well, it takes 30 days, so actually it would be 30t, right? Okay, so actually t, we'll just say that, okay? And so what we end up doing is we do this, we divide 10 right here, divide by 10, and we find that 5 is equal to b, right? So our b, our change is 5, okay, b to the t power. And that's going to come into play when we figure out t being something interesting, right? So our base now is going to be 5. So we're going to write it like this. We're going to write our equation and say that it's going to model that y is going to be 5 times, 10 is what we start with. 10 times 5 to the, well, it takes 30 days, right? So it's proportional, 1/30th times t, right? Our k is 1/30th, right? Because every day it changes, right? Proportional. So that's what we're going to do. Now what we're going to do, okay, and we're going to let, it says we want it to reach 100. So we want our population right here to be 100. So we're going to plug 100 in for y. And we're going to say that 100 is equal to 10 times 5 to the 1/30th t power. Okay? So let's solve this problem. And we're going to solve it for t, because t is going to tell us the number of days it takes to get to 100. So we divide by 10, right? We divide by 10. We get 10 is equal to 5 to the 1/30th power times t, right? And so now what we have to do is we have to get rid of that base of 5. And so we're going to take the natural log of both sides. ln of 10, ln of this whole bad boy right here. And we end up getting ln of 10 is equal to ln of 5 times 1/30th times t, right? That 1/30th and that t drops down when we do natural logs. So what we can do then is we can divide both sides by the natural log of 5, right? Divided by the natural log of 5. And so what I end up getting is that ln of 10 over ln of 5 is equal to 1/30 times t. Now, how do I get t by itself? I have to multiply both sides by 30. Okay? And then those cancel out. And I find that my t is equal to 30 times the ln of 10 over ln of 5. And I can go to my calculator. Okay, I can go to my calculator and actually put those in. And I would do 30 times the natural log of 10 divided by the natural log of 5. And I get approximately 43 days. So, although it took 30 days to reach 50, it would only take 43 days to get to 100. So it's going to grow so much faster, which we know that to be because it's exponential growth, right? Okay. Now, our next problem is going to be using carbon-14 dating. So example 5, carbon dating. Okay. Okay, so I typed out the problem for you. It says scientists use carbon-14 dating, use 5,700 years for its half-life, meaning it takes half, goes down to half amount in 5,700 years. Or yeah. So find the age of a sample in which 10% of the radioactive nuclei originally present has decayed. So if 10% is gone, 90% is less. And so our original problem, remember, is always this, right? Y is equal to Y0 times our base, okay, which in our case is going to be a half. And we know that our 5,700 years is our decay, so we're going to do T over 5,700, right? Okay, so 5,700 leaves 1/5700th of it, right, for every time T, okay? So now if we know that if this original amount is 100%, right, if we think of this as a percent, and now this is 10% gone, that would be 90%, right? What we can do is we can do this. We can say, all right, well, if I let 100% just be 1, 90% is going to be 0.90. And that's going to equal 1/2 times T over 5,700. And my job is to figure out what T is, right? So the way we drop down a power, again, is natural logs, right? So we're going to take the natural log of both sides. Okay? And then I end up getting this. The natural log of 0.9 is equal to the natural log of 1/2 times T over 5,700. Okay? Now, if it was me and I'm solving for T, I'd first take care of the 5,700. That goes away. Okay? And then I'm going to divide that by, so use the color, ln of 1/2, right? Because then those cancel out. Okay? And so that means that our T is going to be 5,700 ln of 0.9 all over ln of 1/2. And that's just a number we can put into our calculator, right? And so what I'm going to do is, okay, I'll just put it in my calculator. 5,700 times ln of 0.9 divided by ln of 1/2, which is 0.5. And I get approximately 866 years old, right? So if 10% of the original number of carbon atoms is present in the nuclei, then the object or whatever it is 866 years old at that point. Okay? Another example of exponential equations that we frequently can use and that scientists use all the time, okay, is something called Newton's law of cooling, right? So his law of cooling, all right, let's write this down. Newton's law of cooling is an exponential equation, right? And so basically it says this: our change in temperature over change in time is really this, right? Which is K is the rate at which it's changing all the time, and T is the time, and T is time after so many seconds, right? And so what we end up getting, right, is if we were to multiply both sides by dt, right, multiply this by dt, and multiply this by dt, you get big D of t, right, is going to be the change in t, which is t minus ts, which we know from here, is equal to negative k times t of ts, right? We got that. And so then if I was going to take the antiderivative of it, it ends up being this, right? Again, this is still dt, so I got to take the antiderivative. I get this. I get t minus ts is equal to our initial t minus ts to e to the negative kt power, right? So because the k is out here, and I'm taking the derivative in terms of t, this is what I end up getting right here, right? And this is called Newton's law of cooling, specifically where this is the temperature at time 0, right? So this is our initial temperature. Initial temperature, in terms of TS, right? And so how much it's cooled, or what the temperature that we're applying some change to, right? Okay, so let's look at an example. Okay, and so this is going to be example 6. So I've typed out the problem for you right here. It says a hard-boiled egg at 98 degrees Celsius is put in a pan under running 18 degree Celsius water to cool. Let's say cool. Okay. So after 5 minutes, the egg's temperature is found to be 38 degrees Celsius. How much longer will it take the egg to reach 20 degrees? Okay. So TS, okay, is our change in temperature amount. And that's our 18 degrees Celsius. That's our TS. We know our initial temperature to be 98, right? And we also know our time is 5 minutes. And so we're going to say T is equal to 5, right? We also know that T is 38 at that point, right? So T is equal to 38. At time T is 38, okay? So going back to our original problem, or our original equation, T minus TS is equal to T0 minus TS e to the negative KT power, right? What we can do is we can plug in some numbers to make it a little bit easier on us, right? Okay, so our original problem, we don't know what our temperature is, but we know that we're taking 8 degrees away from it. That's from the running water. Our original amount is 98. And again, we're taking the 18 degrees from it, e to the negative KT power. Okay, and so we end up finding out that T is actually just equal to, well, 98 minus 18 is 80, e to the negative KT power. And then I'm going to add 18 to it, so plus 18, right? So that's what T is right there. Okay, and so then we said when T is equal to 5, okay, so that, I'll just say check mark there. Okay, that's when I know what T is. Okay, now what I can do is I can figure out what K is, because K is really what we're trying to figure out is how much longer it's going to be using, or figuring out what K is, then we can solve for T, right? We have to solve for K and then for T. So we got to figure out what this is. So at time 5, so when T is 5, okay, this little t is 5, this is going to be 38, right? So we're going to say 38 is equal to 80 e to the negative 5k power plus 18, right? And so what ends up happening if I solve this out a little bit further, okay, what I end up getting is I'm going to subtract 18, I get 20 is equal to 80 e to the negative 5k power, right? Divide by 80, divide by 80. And so I say 1/4, or 0.25, is equal to e to the negative 5k. So solving for k, I'm going to take the natural log of both sides. Okay? And then I get ln of 1/4 is equal to negative 5k, right? And so then I divide by negative 5, I divide by negative 5. And so then that's really just going to be, that's actually what our k is going to be. It's just going to be ln of 1/4 over negative 5. Okay, and actually, if we think about it like this, remember ln of 1/4 is ln of 1 minus ln of 4 over negative 5. And so remember ln of 1 is just 0, and so those negatives cancel out. We get ln of 4 over 5. That's what our k is, okay? Now, that's step 2. We figured out what k is, all right? So now what we have to do is we have to figure out what our t is, right? And so what that means is we're going to go back to our original problem, okay, and say that we want this. T minus Ts is equal to T0 minus Ts e to the negative kt power, right? Now we're going to plug in everything that we know, right? We want our temperature to be 20, right? That's what we want. And so what we're going to do is we're going to say 20 minus the changing temperature, 18, is equal to 98 minus 18 e to the negative, remember k is ln of 4 over 5 times t, right? And so we end up saying that 2 is equal to 80 e to the negative ln of 4 over 5 t, right? And so as I solve this out, right, I get dividing this out would be 1 over 40 is equal to e to the negative ln of 4 over 5t. I take the natural log of both sides, so the ln of 1 over 40, okay, is equal to negative ln of 4 over 5 times t. And so I end up saying t is really just the ln of 40 divided by negative ln of 4 over 5. Right? That's what it is. And so I go to my calculator, and I'm going to have to use good parentheses. So remember, put this in parentheses, put this whole thing in parentheses. So it's going to be ln of 40, excuse me, 1 over 40 divided by negative ln of 4 divided by 5. And I end up figuring out that t is going to be 13.3, and that would be minutes, because remember we had time. Okay. Now my hope is that the problems going forward are going to be a little bit easier. In fact, I'll pick problems that are going to be a little bit easier. Hopefully they're easier for you to follow along. You know, some of this got to be a little kind of a jumbled mess at times, but hopefully this is some of it makes sense for you. Hopefully it's a little bit more plug and chug problems than theoretical problems, and we're able to do these. So good luck. Good luck on your assignment.